Welcome everybody. Now we are going to discuss about flip-flop conversion. Already we have seen how to convert SR flip-flop into JK flip-flop. We have seen how D flip-flop can be obtained from JK, how T flip-flop can be obtained from JK. So now let's discuss other flip-flop conversion. So in order to convert some given flip-flop into desired flip-flop, so it is required to design flip-flop conversion logic. Now let's see one problem. Suppose we want to convert SR flip-flop into D flip-flop. Already we have seen implementation of D flip-flop. How we can design D flip-flop. So D flip-flop can be obtained either from SR flip-flop or JK flip-flop. How? So we have seen that we should use one inverter between inputs of SR flip-flop or inputs of JK flip-flop. So we can keep one inverter between S and R inputs of SR flip-flop, so we will get D flip-flop. Or if we place one inverter between J and K inputs of JK flip-flop, we will get D flip-flop, right? So already we know this point. Now let's see step by step how SR flip-flop can be converted into D flip-flop. So see, first step will be you should draw block diagram like this. We have given which flip-flop? SR flip-flop. We want to convert that SR flip-flop into D flip-flop. So here for that what we have to do, we have to design one flip-flop conversion logic. So this flip-flop conversion logic will take D as input, Q and Q prime. What is Q and Q prime? So these are the outputs of given flip-flop. So in this case given flip-flop is SR flip-flop. So by using this Q, Q prime and D, this flip-flop conversion logic will generate some outputs. So the output which are generated by this flip-flop conversion logic should be sent to inputs of given flip-flop. So one output of flip-flop conversion logic should go to S and other output should go to R. So now let's see how this flip-flop conversion logic can be designed. It's very simple. Just there are number of steps which we have to follow in sequence. So let's see now step number 1. So step number 1 is write truth table of D flip-flop. Okay. So first of all you have to write truth table of D flip-flop. We have given SR flip-flop and we want to convert that SR flip-flop into D flip-flop. So here we will require two tables. So we will require truth table. Okay, we will require truth table of D flip-flop and we will require excitation table of this second flip-flop, that is SR flip-flop. Please try to understand. We have SR flip-flop, we want to convert it into D flip-flop. So now I can say that this is my first flip-flop. So here we will require truth table of this first flip-flop and you will require excitation table of this second flip-flop. So first of all let's write truth table of D flip-flop. So truth table of D flip-flop will have these three columns. So first one is D, second one is Qn and third one is Qn plus 1. Now here in this truth table which will be the inputs? So D and Qn. What is Qn? Present state of D flip-flop. So D and Qn will act as an input. And what will be the output? Output will be Qn plus 1. So Qn plus 1 means next state of D flip-flop. Right. So first of all we will try to write this truth table. So in order to write this truth table, first of all what you are supposed to do? You are supposed to write all input combination. So in this truth table which are the inputs? D and Qn. So these two are inputs. So for this two column, how many combinations are possible? So by using this two input, we will get 2 raised to 2, that is 4 combination. So let's write those 4 combination: 0 0, 0 1, then next should be 1 0, and last one should be 1 1. Okay. Now already you know working of D flip-flop. What happens in D flip-flop? Okay. So in D flip-flop, whatever input we apply, same will become output. So see here what is input? 0. So what will be the output? What should be the next state of D flip-flop? Right? So in case of D flip-flop I can say that next state will not depend upon present state. Okay, so in order to write this next state I should not consider present state. In case of D flip-flop, in D flip-flop output follows input. So here input is 0. So what should be the next state? 0. Here input is 0. What should be the next state? Again 0. Here input is 1. What should be the next state? 1. Here input is 1. What should be the next state? 1. So in this way, first of all you should write truth table of this first flip-flop. After that, see which is second step? Add two columns S and R in truth table of D flip-flop. So this is truth table of D flip-flop. Now in this truth table we are supposed to write two columns. So which are the two columns? One is S and second one is R. Why we are adding this two column? Because we have given SR flip-flop. That's why we have to add these two columns. Now see, this table will become like this. Okay, so just I have modified now this truth table. I have added two more columns. One is yes and second one is R. Now step number 3. Step number 3 is combine excitation table of SR flip-flop in the table obtained in step number 2. So now first of all let us see excitation table of SR flip-flop. So excitation table of SR flip-flop is like this. Okay, already we have seen how to obtain excitation table of different flip-flops. So actually this excitation table can be obtained from truth table. So this is excitation table of SR flip-flop. So this excitation table has to be combined with the table that is obtained in step number 2. So in step number 2 we obtain one table like this. So now what we have to do, we have to combine these two tables. So how to combine these two tables? So see, now you should neglect this D. For some time, just keep this first column of this particular table aside. Okay, now just focus on Qn and Qn plus 1. So here what is Qn and Qn plus 1? 0, 0. What it indicate? It indicate that present state is 0 and we want next state 0. So for that, what should be the value of S and R? So see excitation table of SR flip-flop. So we will get this information from excitation table. Present state is 0, next state is 0. So what should be the value of S and R? So it should be 0, okay, and don't care. So that 0 and don't care will come here. Then consider next row. So here what is present state? 1. What is next state? 0. Okay. So present state is 1, next state is 0. So what should be the value of S and R? 0 and 1. So write that 0 and 1 here. Then consider next row. Here present state is 0, next state is 1. So present state is 0, next state is 1. So we have present state as 0. We want next state of SR flip-flop as 1. So what should be the input? So input should be S is equal to 1 and R is equal to 0. So S is 1 and R is 0. Okay. Now consider last row. So last row says that present state is 1 and next state is 1. So for that, what should be the S and R? So present state is 1 and next state is 1. Okay. So for that, what should be the S and R? So S should be don't care. So S can be don't care, means value of S can be either 0 or 1. So S is don't care. And what about R? So R is 0. So in this way, what you have to do, you have to combine this excitation table of SR flip-flop with the table which we obtain in step number 2. Now let's see step number 4. Again, please try to understand what we want to do. We want to design this flip-flop conversion logic. So this is one combinational circuit. Okay, this is one combinational circuit which we want to design. So in order to design this particular logic, in order to design this particular combinational circuit, we will require truth table. We have already seen how to design combinational logic. So in order to design combinational circuit, we will require truth table. So see how that truth table is obtained. So let's see step number 4. So neglect Qn plus 1. So in step number 4, what we have to do? We have to simply neglect Qn plus 1. So which Qn plus 1? So the Qn plus 1 which is present in this particular table. How we have obtained this table? So we have obtained this table in step number 3. Okay, so now in this table, what you have to do? Just you have to neglect this Qn plus 1. You have to focus on column D, Qn, S and R. Right? So this D, Qn, S and R. So these 4 columns will give you truth table which is required for designing this particular flip-flop conversion logic. So see, design required combinational circuit. So which combinational circuit we want to design? This particular combinational circuit. So in order to design this particular flip-flop conversion logic, use D, Qn as an input. Okay, so in this table these 2 columns are there, so D and Qn. So use this D and Qn as an input and S and R as an output. So after step number 4, we will get a table like this. Okay, so now I can say that this is truth table for that flip-flop conversion logic. So here you should consider D and Qn as an input and S and R as output. So step number 5 is draw K-map for S and R. So there are 2 outputs, so that's why we have to draw 2 K-map. What type of K-map? 2 variable, 3 variable, 4 variable. So see how many inputs are present. So in this truth table, 2 inputs are there. One is D and second one is Qn. So that's why we should use 2 variable K-map. So first of all, let's draw a K-map for yes. So K-map for yes will be like this, right? So see whatever information present on this truth table is shown in this K-map. So yes is 0, 0, 1, don't care. So 0, 0, 1, don't care. Okay. After that we have to make the group. So this pair is possible in this particular K-map. After that you are supposed to write expression for yes, output is yes. So yes is equal to, so what will be the term that will correspond to this particular group? So here we are getting only one group. Okay, so for that one group we are supposed to write the term. Okay, and that term should be a product term. So for this group, which variable is changing? Whether D is constant? Yes, D is constant. What is value of D? D is 1, so that's why D will come here. What about Qn? So Qn is changing. Here it is 0, here it is 1, so discard Qn. So I can say that yes is equal to D, right? In same way you can draw K-map for R. Okay, so this is K-map for R. Here this group is possible, and from this group you have to obtain expression for R. So R is equal to D prime. So now we have obtained two expressions, one for yes and other for R. Now see what you have to do. So this was our original block diagram. So now in this block diagram you have to make the change. We have got what is equation for yes. So yes is equal to D. We have designed this particular flip-flop conversion logic, and we have generated two output. One is for yes and other one is for R. So what input I should apply to yes? So yes is equal to D, means this D should be directly connected to yes. And what about R? So R is equal to D prime. So here by using NOT gate you should obtain D prime, and then that D prime should be given as input to this R. So see, in step number 6 what you have to do, you have to draw logic diagram for flip-flop conversion. So this was our original block diagram. So here now what we will do, we will replace this particular flip-flop conversion logic with the expression that we got in previous step. So that expression was yes is equal to D, so that's why D is directly given as input to yes, and R is equal to D prime, so that's why R is given as input to NOT gate, and output of this NOT gate, that is D prime, is applied to R. So now this combined circuit, that is SR flip-flop along with this NOT gate, is going to act as a D flip-flop. Now let's check. So if D is equal to 0, if D is 0, then what happens in D flip-flop? In D flip-flop, if D is 0, then what next state is expected? So next state of D flip-flop should be 0. So now let's check whether it is happening here. So D is 0, so what will be the value of yes here? So yes will be 0. What will be the value of R here? So D is 0, output of NOT gate will be 1, R will be 1, right? So yes stands for set, R stands for reset, so R is 1. So what should be the Q? So Q will be 0. Getting, because R is 1. So whether we have got expected result, we have applied input 0, and in D flip-flop we are expecting output 0, so we are getting that output. Now consider second case. Suppose D is 1. So we know that in D flip-flop if D is 1, then output will be 1. Output should be 1. So here D is 1, so yes will be 1. What about R? So output of NOT gate will be 0. So R will be 0. So yes is 1, yes stands for set, so that's why what will be the output here? So output will be 1. So we applied 1, we given 1 as an input, and what output we are getting in D flip-flop, or what is next state that we are getting in D flip-flop? It is 1. So this is D flip-flop. So in this way what we have done, we have converted SR flip-flop into D flip-flop.